For this lesson, we're going to be continuing with our look at various ways to combine functions. This particular combination, which is quotients of functions, where we're doing a function divided by another function, is very much a review in many ways because we've already touched upon this in an entire unit where we were looking at rational functions. In particular, we were looking at rational functions of a polynomial divided by another polynomial. Now, obviously, this is a much wider array of functions. We're not restricting that f or g have to be polynomials here, but the idea, the single most important change between this lesson and the previous lessons where we looked at addition and subtraction or multiplication of functions is the presence of a denominator and the fact that we have an additional restriction there, which is the denominator cannot be equal to 0. So let's start off by taking a look, as we have done in a number of cases already. Let's look at a very simplistic example where in this case the function f is defined as this set of 4 points and the function g is defined as this set of 3 points. The first thing we're going to do is find the domain of fg and this new function we're creating, f divided by g. So the domain of f itself, that would be the x-coordinates of these points. So that would be 1, 2, 4, and 5. And I'll just represent that using set notation. And the domain of g I find in a similar way. It is the x-coordinates 2, 3, and 5. And from there we get the domain of f divided by g. And if we press ahead the way we have done up until this point, then we're looking for overlap. We're looking for the intersection. And so I don't have a 1, but I have a 2. I don't have a 4, but I have a 5. So from previous definitions that we've looked at, it would seem that the domain of f divided by g is 2 and 5. But obviously the way I'm qualifying my language here might give you a bit of a hint that it's not quite as simple as that. But we're going to leave that as is, and then we're going to come back to it after we go through and do this f divided by g. Now, since I'm using set notation, I'm not going to say f of x divided by g of x. I'm not creating a function here. Well, actually, I'm sorry, it is a function, but I'm not creating an algebraic version of this function. I'm just creating a list of points. So since the domain, as I found it in part A, were the two values 2 and 5, then I anticipate that my 2 points are going to have x-coordinates. One will be x equals 2 and one will be x equals 5. But let's take a look at those two values. When x is equal to 2, f divided by g is going to be what? And when I say f divided by g, I mean the y value. I could even write this way. I could say the y, let me clean that up a bit. I could say the y value of f divided by the y value of g when x equals 2. So when x is equal to 2, the y value of f is 0. When x is equal to 2, the y value of g is negative 4. And 0 divided by negative 4, 0 divided by anything except for 0, is just equal to 0. So that's perfectly fine. So one of our points is 2, 0. When x is equal to 5, if this is the last one we're looking at, then if something's going to go wrong, it's going to go wrong here. So my y value of f over my y value of g is equal to the y value of f for x equal 5 is 11, and the y value of g for x equal 5 is 0. And 11 over 0 is undefined. So we don't have a value that we can associate with that. And it's not correct to do something like this. You can't say that it is made up of the point 5 comma undefined. Nor can you do something like put, sorry, not 10 over 0, 11 over 0 here. That's just as bad. It's undefined. We're not allowed to have this representation as part of a solution. So as a result, it turns out that this is actually incorrect, which means this was incorrect. And the reason why we should have recognized that 5 was not allowed is because here we have a y value equal to 0 in the denominator. But we're not allowed to have y values of 0. We're not allowed to have values of 0 in the denominator. So there's a pretty large hint when I'm looking at my definition for g. I could have taken a look at the y values or the range values, and wherever I have a 0, that domain automatically gets excluded. So now I have to fix this a bit. So my domain of the combined function should have just been 2, and my domain, or sorry, not my domain, my definition of the combined function, f divided by g, is simply one point, has an x coordinate of 2, and it works out to be a y coordinate of 0. And so I comment on that here. I just make a note. I said it verbally before. So since g of x is in the denominator, we have to avoid division by 0. So when we do our domain of the combined function, in this case it's the quotient, it's the intersection of the domain of f with the domain of g. I take the intersection of those two domains, but then I also ensure that g of x is never equal to 0. And when I say g of x is never equal to 0, I am referring to the y coordinate in the definition of g. We can't have any y coordinate equal to 0. Now for this next example, things are going to look a little bit different, because in this next example we are looking at an algebraic notation. So we're not looking at a list of points, and a list of points is also what we'd really be looking at if we were looking at a graph. Here we have an algebraic notation. So for this one, rather than worrying too much about the domain, I still have to come up with an algebraic representation of my quotient. So I'm just going to go ahead and start with that. So f divided by g of x is f of x over g of x. That's the definition. And then I move forward from there. F of x is this quadratic, x squared plus x minus 6, all divided by the square root of x plus 3. I chose this quadratic specifically because it actually can be factored into x plus 3 and x minus 2 over the square root of x plus 3. And although it's not our typical situation where we're looking at having a common factor in the numerator and denominator, we actually do have that. And the way I'm going to point that out to you is that this is x plus 3 to the exponent 1. X minus 2 is also to the exponent 1, but I'm not going to highlight it. And in the denominator, x plus 3 to the 1/2 is the same as the square root of x plus 3. And so now what I'm going to do is I'm going to combine this x plus 3 to the 1 and this x plus 3 to the half using our laws of exponents, so I can subtract. These are the same bases, so I can subtract the exponents, and I end up with x plus 3 to the 1/2 times x minus 2. And you might choose to rewrite that as the square root of x plus 3 times x minus 2. Now in doing all of this, I have actually caused the radical, but in this case it was the point is it was a term in the denominator is no longer, I don't have a denominator anymore. My denominator is 1. So now how do we handle this when we start thinking about the domain? Well, the first thing we do is you want to go back to your original expression where you first introduced the quotient, and in this case a denominator. So this immediately tells us that the square root of x plus 3 cannot be 0, or normally I would expect you to go just straight to the answer here, which is x cannot be equal to -3. When we worked through here and got this common factor of square root of x plus 3, when we got to this point, what we had done was we have created a hole at x equal -3. So if you're graphing this and you're asked to do a graph, you could actually find the coordinates of this hole, and you could put that on your graph. Now, we're not doing anything like that. I just wanted to point that out to you. And now let's take a look, and maybe I'm going to come back up here just to the original functions first of all. So let's take a look. What is the domain of f? The domain of f in this case is simply x member of the reals. There are no restrictions on this quadratic. The domain of g is x member of the reals such that x is greater than or equal to -3. But we've introduced this additional restriction, which is that x cannot be equal to -3. So what we had said before about x greater than or equal to -3, when I take those together, so this combines with this, and as a result we end up with x must be greater than -3 as these two things combine together. And so that's where we end up with our overall, our domain of f divided by g becomes x member of r. X is a real number, but now I have to say that x is greater than -3, which is that combination that I did before. Okay, now let's take a look at a famous is probably not the right word for this, but this is a fairly well-known example of a combination of functions. It produces a fairly interesting result, and there are some physical phenomena, and so this is something that I'm familiar with from physics, but it's also studied in mathematics because it has some interesting properties. I've got sine x over x. Now sine x has a domain of x member of r, x has a domain of x member of r, but because we're dividing by x, then fairly obviously we can't have x equal to 0. So we have this restriction. And in the case of this graph, then when sine x over x, each of those is equal to 0 when x equals 0, so we end up with that situation 0 over 0. Now there's some very interesting math that occurs around that value, so I'm not going to get into too much depth about it right now. It's not as simple as our discussion, just the idea of having a hole, for example. But we have this interesting graph, this interesting shape, and if you think about it, if you think about this denominator, although we're dividing by x, it's actually more useful to think of this as multiplying. So it's more useful to think of this as sine x times 1 over x. And the reason is because there is this kind of reciprocal function shape going on. And that's where that shape is coming from. It's coming from that reciprocal function. If we take a look at the reciprocal of sine x over x, which is x over sine x, we still have the same problem when x equals 0. This becomes a 0 over 0. But we have additional issues because sine x actually is equal to 0 in a number of locations. It's actually periodic in nature. So our restriction ends up being this periodic restriction based on multiples of an integer. And you can see pretty clearly where the asymptotes are coming in here. So there's an asymptote. I didn't quite hit it right on. And there, and so on. And we have these asymptotes occurring at intervals of pi. And just as I said before, right here, it's not so simple as just, it's not like when we did polynomial divided by polynomial and the idea of a hole here. There's something more complicated happening here. And so I'm not going to trivialize it, but this is also an interesting thing that we probably will look at in our next unit or our next course in calculus. Now this particular function we don't actually see very much. The one on the previous page comes up fairly often, sine x over x, whereas this one, other than for the purposes of this lesson, I don't particularly recall seeing it before. Now, the other interesting thing I want to point out here again is just this getting practice about seeing the different functions as they appear and how they're combined together. So these blue lines that I've put in here, these are blue lines y equal x. So this is the line y equal x, and this is the line y equal negative x. And that's this linear function. And then, of course, you can see the presence of the sinusoidal. Whether you recognize that it's sine or cosine is almost irrelevant. The point is you see that there's something periodic happening here. So that's something you need to develop some experience for, and that will get easier as you do more of it. Let's wrap things up with doing a quotient here. And so we're going to run into some of the same factors, some things we've seen before. For example, when selecting my domain, the domain of f goes below -1, but the domain of g starts at, sorry, I said below -1, goes below 1, but the domain of g starts here at 1. So this is where I do my first division. I do f divided by g, which is 0 divided by 2, which gives me a point at 0. And I'm going to do a closed dot here. I'm going to assume that the red line includes 2. So I'm assuming this is included here, and I'm assuming this point is included there. Now, what about when x equal 2? I've got 1 and 1, so 1 divided by 1 is simply equal to 1. At x equals 3, I've got 2 divided by 0. So we know something interesting is happening here. So 2 divided by 0. So what could be happening here? Well, with 2 points here, that's not enough to know. So what I can do is make use of something we've done a number of times in the past, which is let's take a look at some values that are very close. So for example, let's say that is the y value of 1.9, and that would be the y value of about 0.1. So what is 1.9 divided by 0.1? 1.9 over 0.1 is actually equal to 19, which is way, way up here. So that tells me that this, well, I didn't do that very well. Let's try that again. That tells me I'm going to get something that looks like that. And that is a pretty clear indicator of an asymptote at x equals 3. And that's going to help me because when I do my next values, for example, here at x equals 4, I have 3 divided by -1, which is equal to -3. And I have 4 divided by -2, which is equal to -2. And I can do the same kind of process here where, for example, this is around 2.1 and this is around -0.1. So that's going to give me -21, which is way down here. So this one is going to look something like that, heading towards the asymptote. Now, that might be a bit of a surprising result, but if you think about what f of x and g of x started as, f of x is the straight line x minus 1. G of x is the straight line 3 minus x. And if I take the quotient, x minus 1 divided by 3 minus x, I actually end up with a rational function. Not the reciprocal, not 1 over x, but I end up with x minus 1 over 3 minus x. That's, let's call that h of x. And that is a rational function, and it's going to, in this case, has an asymptote at x equals 3. And the overall shape is the same as that very familiar reciprocal function shape that we've seen in the past. And I think that's it for this lesson.